Our task in this problem is to find all the currents and voltages in this network. As indicated, there are 3 voltages and 6 currents in this system. Our approach to this problem will be to first find the total resistance seen by the source and use it to find I1, and then apply Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law, current division, and voltage division to determine the remaining unknown quantities. Starting at the opposite end of the network from the source, the 2K ohm and the 4K ohm resistors are in series, which give us 6K ohm. And that combination is in parallel with the 3K ohm resistor, yielding 2K ohm. And that reduces the network to this. Continuing with the same approach, the 10K and 2K ohm resistors are in series, which gives us 12K ohm, and that combination is in parallel with the 6K ohm resistor, yielding 4K ohm. Continuing with the same logic, the resultant 4K and existing 4K ohm resistors are in parallel, which gives us 2K ohm, and that reduces the network to this. Now, I1 and V1 can be easily obtained using Ohm's law. I1 is equal to 48 divided by the series resistance of 2K plus 2K, which is equal to 12 milliamps. And using Ohm's law, V1 is equal to 2K ohm times I1, or 12 milliamps, which is equal to 24 volts. Or you could use voltage division to obtain the same answer. Either way, V1 is 24 volts. Reversing the process now and returning to the original circuit, once V1 is known, 24 volts, I2 and I3 can be obtained using Ohm's law. I2 is V1 divided by 4K ohm, which is equal to 6 milliamps. I3, which is equal to V1 divided by 6K ohm, and that is equal to 4 milliamps. I4 can be obtained using Kirchhoff's current law at the node A. I1 is equal to I2 plus I3 plus I4, and we know I1 and I2 and I3, therefore I4 is simply equal to I1 minus I2 minus I3. I4 can now be calculated and is equal to 2 milliamps. The voltage of V2 is then V1 minus the voltage drop across the 10K ohm resistor times the current through it, I4, or 10 times 2, which is 24 minus 10K times 2 milliamps, which is 4 volts. Returning now to the original circuit, knowing V2, I5 can be derived using Ohm's law. I5 is equal to V2 divided by 3K ohm, which is equal to 4 divided by 3, which is equal to 1.33 milliamps. Also, I6 is equal to V2 divided by 2 plus 4K ohm, which is 4 divided by 6, which is equal to 0.67 milliamps. Current division can also be used to find I5 and I6. Current divider rule can also be used. I5 is equal to 2 times the quantity 3 plus 4K ohm divided by 3 plus 2 plus 4K ohm, which is equal to 12 divided by 9, giving us 1.33 milliamps again, and I6 is equal to 2 times 3, or the quantity 3K ohm divided by 3 plus 2 plus 4K ohm, which gives us 0.67 milliamps. Finally, V3 can be obtained using Kirchhoff's voltage law. V3 is equal to V2 minus 2k ohm times I6, which is equal to 4 minus 2k ohm times 0.67 milliamps, which is equal to 2.67 volts. The network has now been solved for all currents and voltages. This brings us to the end of this problem and its solution. If you want the full range of problems and their solutions, you can find them at my Stan store at this web address. And finally, my newest course that I just added, Bridging the Gap Between Theory and the Practical. This course was developed specifically to solve the pain point of those newly introduced to the power industry. Whether you're an engineer, technologist, or electrician, this course is designed to give you a preview of what's ahead of those just leaving the halls of book learning and entering into the electrical power industry.